Doc here with another physics tutorial for Physics 101 Light and Visual Phenomena. We're going to find a home for the 6 colors we study in our class, the basic 6 colors, which consist of 3 colors for primary rules of addition and 3 colors for primary rules for subtraction. Let's review these colors. The big 3 for addition: blue, green, and red. Blue can be thought of in the idealized model as the first third of our spectrum when we plot the amount versus the wavelength. Green is the middle third, and red can be thought of as the third third. When we combine these together in various ways, we get the compound colors cyan, magenta, and yellow. Blue and green, the first 2 thirds, gives cyan. Blue and red, first third and the third third, gives us magenta. And the last 2 thirds, green and red, gives us yellow. Notice that each of these compound colors is missing one of the primary colors from addition. For example, cyan is missing red, magenta is missing green, and yellow is missing blue. Those pairs are called complementary colors. So red and cyan are complements, are complementary pairs. Magenta and green are complementary pairs, and so would be yellow and blue. This gives us the big 6. Blue, green, and red, the 3 primary colors for addition. Cyan, magenta, and yellow, the 3 primary colors for subtraction. And together, it's the big 6. Let's find a home for them in our cul-de-sac. Since we have 6 houses, we'll need to divide this up into 6 regions. We're going to put the houses where the angles are, there, where that line is here, this line there. And notice that when you have a circle, like a pizza pie, and divide it up, let's say 6 ways, that you get 60 degrees for the angles of each of the pie-shaped regions. If you have 360 degrees in a circle, divided by 6, you get 60 degrees per piece. The convention is to put red down first, and we're going to put the complementary colors, which are really opposites, across the street. Let's get that complement across the street from red, cyan. And if we think Roy G. Biv counterclockwise, yellow, Roy, we're going to skip orange because orange is not one of the big 6. We have yellow, and across the street from yellow, blue, and next would be green. And across the street from green is magenta. Many years ago, I read an article where the researcher claimed that in the old days, when they said Roy G. Biv, that their blue was what we call today cyan, a blue-green, and what they call indigo is what we call blue today. When you think of it that way, it solves the mystery as to who sees a color between blue and, like a sort of a violet, an indigo. So I'm going to use that idea where this is Roy G. Biv, where we skip the orange. Red, we have yellow, orange would be in between, that's Roy. There's G, and B, the old blue is our cyan, the old indigo is our blue, and we replace the violet with magenta, and we have a nice color wheel. This color wheel can also be understood from our color addition rules, in a sense by luck, because I picked the blue at the lower left corner and green at the top and red at the right. I did that years ago because I like blue as a short wavelength. I put that left, I put green as the middle region of the spectrum in the middle, and red long wavelength over to the right. But by doing this, watch the nice relationship to the conventional color wheel. If you take green and blue, you get cyan. When you add them together, additively mixture. Additively means we're using primary colors for addition. We're shining beams on a screen, and they're overlapping beams. Green and red overlap, give yellow. Blue and red overlap, give magenta. And when all the beams overlap, you get white. Notice that we have red living here. Across the street from red is cyan. Red's neighbor is yellow. Across the street from yellow is blue. The yellow neighbor is green. And across the street from green is magenta. Kind of what we have here. Red across the street is cyan, its neighbor yellow across the street is blue, and the neighbor green across the street is magenta. This color wheel has even more properties. If we look at the 3 primary colors for addition, blue, green, and red, if we add blue and green, we get the color in the middle between the 2, cyan. If we add green and red, we get yellow. And if we add blue and red, we get magenta. Now, if we take the primary colors for subtraction and combine those in a subtractive way by overlapping filters, then a cyan filter overlap with a yellow filter, a subtractive mixture, gets you the color in the middle here, green. When you overlap the cyan and magenta filter, the subtractive mixture, you get blue, and subtractively mixing, yellow and magenta gives red. Why does it work this way? Well, look at cyan. It consists of green and red. Green and blue. When you make cyan, you have greens and blues. The second third of the spectrum and the first third of the spectrum. So greens and blues gives you cyan. When you make yellow, you have greens and reds. So when you look at a yellow filter, it lets green and red go through because that's what yellow is. Yeah, yellow consists of greens and reds. When you have a cyan filter, it lets through greens and blues. When you overlap these two filters, the color that's in common that can pass gets through both. That would be the green. So that's an interesting way to see how these color mixing schemes work for addition and subtraction. Here's a tricky question I asked students years ago on exam, and maybe we'll ask you. What is the angle for orange? It's not so bad when you understand a color wheel pretty well, because the orange, if you have Roy G. Biv, orange is between red and yellow, and that would have to be 30 degrees. See? In fact, let's make the question even harder. What is red-orange? Well, red-orange would be between red and orange. It'd be 15 degrees. See? So now we're answering hard questions in an easy fashion because we know the color wheel so well. Good luck studying. Off for now. See you later.